Assalamualaikum. Now we are going to continue our chapter number 4, and hopefully it will be the last lecture of our chapter 4. And the topic of our lecture is basically linear delay model. Before we're going to discuss about the linear delay model, firstly we have to know about what is the normalized delay. Express the delay in a process independent form. Circuits can be compared based on the topology rather than the speed of the manufacturing process. So basically we observe that the delay of an ideal fan out of one inverter with no parasitic capacitance is basically 3RC. It's very important to know about that. Then the normalized delay can be related with the inverter delay is T is equal to TPT divided by tau. So hence the delay of a fan out of each inverter can be written in the normalized form as diffusion capacitance equal to gate capacitance, and then it becomes D is equal to H plus 1. So what is the linear delay model? The RC model showed that the delay is a linear function of fan out of a gate. Designer simplify the delay analysis by characterizing a gate by the slope and the y-intercept of a function. So here we will very clear that we are going to use a graphical representation where we are trying to find out the value of the slope. Okay, and LDM normalized delay is expressed in terms of two components of the delay. D is equal to F plus P. What is F and what is P? P is basically a parasitic delay, and it is the time for a gate to drive its own internal diffusion capacitance without any load. And F is basically represented as the ratio of the effort delay to the ratio of the stage effort, and it all depends on the H and G. So F is basically G multiplied with the H. So these terms are very important. H is called the fan out or the electrical effort, and it is basically the ratio of the capacitance of the external load to the input capacitance of the gate, to the external load to the input capacitance of the gate, and the complexity, which is called the logical effort, and it represents G, and that represents that complex gates have greater logical efforts, indicating that they take longer to drive a given function. So linear delay model including these two important equations: D is equal to F plus P. P is the parasitic delay, F is the fan out, P represents the capacitance of a gate that drives it to the internal diffusion capacitance, and F is basically represented into GH, and H is basically the fan out, and fan out represented as C out over C in. So let's start with a very basic example, that is the example of our inverter. So the logical effort is basically the ratio of the input capacitance of the gate to the input capacitance of the inverter, delivering the same output current. So measure from delay versus fan out plots. We are going to take a graphical representation and then estimate by counting the transistor width. So the input capacitance of this simple inverter is 3. Then we can see our logical effort is 3 by 3, it means 1. So in case of the 2 input NAND gate, the input capacitance is going to be 4. So we can say that G is basically represented as the logical effort. So the logical effort is basically the ratio of the input capacitance of the gate to the capacitance of the capacitor. So input capacitance of that particular gate is 4 and the input capacitance of the inverter is 3, so divided by 3. So in this case the input capacitance of the gate is 4 plus 1 5 and it divides with the inverter input capacitance, that is 3. So this is the logical effort estimation. The catalog of the logical effort of a common gates are given in this table: inverter NAND NOR, tri-state XOR and XNOR. So here you can find out the value of the logical effort with the help of the number of inputs. So what is the parasitic delay? That's very important. The parasitic delay of a gate is the delay of that particular gate when it drives zero load. So we can say that it can be estimated with the RC delay models. The inverter has 3 units of the different capacitance on the output, so the parasitic delay is basically 3 RC, because we can say that it is the and what happens to the 3 input NAND gate or the NOR gate? We have 9 units of the different capacitance on the output, so the parasitic delay is 3 times as great. A crude method for hand calculation is to count only the different capacitance on the output node, so we will get the value of the parasitic delay. So here is the catalog of the common gates in which we say that it's a multiple of inputs. So let's move toward to find out the value of the delays with the help of the linear delay model. So let's take the example of our inverter. For the inverter, we know that the logical effort is 1 because the input capacitance is 3 and we divide it with the capacitance, that is also becomes 3, so it have the value of 1. The parasitic delay in case of the inverter is 1. So these are the basic delay equations: T is equal to plus P, parasitic delay, in which we know F is equal to GH. So G is 1 and P is also 1. So we have the value of D is H plus 1. From this figure you can see that here is the inverter line. G is 1, P1 and D is equal to H plus 1. Then if we draw a slope, then we will get the value of slope is 1 and slope is equal to tan theta, so theta become 45 degree. In case of our 3 input NAND gate, for the 3 input NAND gate, we know that our logical effort is 5 by 3 and the parasitic delay is 3. So if we have seen it through the graphical representation, then we will get that the tan theta become 5 by 3, that is the slope of our 3 input NAND gate. So from here we can find the value of theta, and at that point we get 59.04 degree. Let's move toward the example. Our problem states that estimate the frequency of the n-stage ring oscillator. To find out the frequency, we need to find out some basic parameters, including the logical effort, electrical effort, parasitic delay, and stage relay. How we will calculate it? We get it through this. It's a basic simple inverter, and we know that the logical effort of inverter is 1, and we know the formula of the electrical effort, that is C out over C in, then we again find the value of 1. And the parasitic delay, the different capacitance is also 1 and the stage relay is basically 2. So for the frequency we have the formula 1 by 2 and D. D is always 2 is 2 in this case, so it becomes 1 by 4, and where n is the number of the stages. If we have get the 31 stages, then we can say that our frequency is approximately equal to 200 megahertz. So it's all about today, and it's your lecture program in which you are supposed to find out the value of this particular value of the frequency of that So it's all about today. If you have any question, you can ask freely.